Hello, my name is Aniruddha Vijay Vyavhare and I am presenting a literature review on hardware security for embedded systems. Earlier, designers thought security as an additional feature to cost, performance, and power, while today it is now considered to be a new dimension to the embedded systems design. Designers earlier thought only software is loophole to many of the attacks, considering hardware to be secure. As embedded systems can affect changes in the physical world, it has become vulnerable to physical damages, cyber attacks, etc., that can cause significant disruption to the society. Taking all these things into consideration, hardware security for embedded systems has now become a serious concern. The entire embedded systems design flow, including the system architecture design, processor design, implementation, and logic design, should be protected with right security solutions. Appropriate hardware security measures should be adopted during the architecture design of an embedded system. As embedded systems play a crucial part in myriad of applications, it comes with a caveat to take different approaches to make the system secure, covering all aspects of embedded systems design. As said earlier, I have considered a top-down approach to discuss about hardware security for embedded systems. The highest level discusses about hardware security at application level in my survey. I have focused on hardware security and its measures on the most booming embedded system application, Internet of Things. As FPGA today holds a promising place in many of the high-end embedded systems applications, one step down I have discussed about FPGA level security. Coming down to the core of any embedded systems applications, I have discussed hardware security for memory and integrated circuits. Integrated circuits form an integral part of any embedded system application. The emergence of hardware trojans or malicious circuits inserted into integrated circuits during the manufacturing process poses a new security threat to the systems that rely on integrated circuits. Hardware trojans are malicious and cause serious issues to the design, functionality, and stability of the integrated circuits. As a result, engineers that design the software for their systems need to employ tools which give a deep and in-depth understanding of the architecture of the integrated circuits. With this approach in mind, the designers not only should code the software that sustains physical attacks or malicious software attacks, but also attacks from the substandard counterfeits and malicious IC logic. Security threats include counterfeiting, reverse engineering, tampering to insert malicious logic such as trojans or kill switches. Real-time IC monitoring proposes to use sensors in the integrated circuits to monitor the side channels to provide real-time analysis of active circuits. This security measure proposes to intentionally permit noise in certain regions of ICs, which in turn will result in voltage fluctuations caused by local circuits, and traces introduced by undesired circuits will become observable. Circuits that are intended to perform a function are always located close to each other. Thus, data paths are most vulnerable to attacks from the adversaries. Splitting the functional circuit blocks into subblocks provides an additional benefit of placing circuits on two separate device planes, which enables the usage of two different foundries to produce each die, thereby reducing the risk of hardware trojans. Attacker can physically attack the external memory in three ways. Spoofing. Attacker replaces an existing memory block with an arbitrary fake one. Splicing. Attacker replaces memory block at address A with a block at address B where A is not equal to B. Replay. A memory block located at a given address is recorded and inserted at the same address at a later point in time. This off-chip memory protection mechanism is based on advanced encryption standard Galloy countermode to provide confidentiality and integrity protection for data and programs transferred from processor to off-chip memory in embedded applications. This mechanism, while securing the off-chip memory, reduces the processor's inbuilt memory overhead as well. It involves dynamic switching between the two modes. One mode processes the data and programs, while the other mode processes the cryptographic parameters. This mechanism with AES algorithm uses universal hashing over binary Galois field to provide authenticated encryption. The figure shows a secure computing model of AGI's protection mechanism. This is a processor-oriented memory security approach which involves protecting the program against physical attacks in three stages, that is, before the program is executed, during execution, and during processor mode transitions. This model involves all trusted components embedded in a single chip secure processor. It provides a tampering-proof protection which is active when it's powered on. Secret key is embedded in secure processor through PUFs as non-volatile memory option is not cost-effective and also easily prone to attacks. The data integrity is maintained by the integrity verification block during off-chip memory operations. This mechanism enables confidentiality and integrity of data between a standard processor and external memory by adding the integrity checking capability to a block encryption algorithm. It involves adding a tag to a data value before ciphering. In read-only operation, the tag contains the memory address to prevent splicing attacks, while in read-write operation, the tag contains the data and memory address which prevents the replay attacks. The systems confirm the maintenance of the data integrity by comparing the deciphered tag and the original tag concatenated with the data. In the coming section, we are going to discuss the vulnerabilities of FPGAs to different attacks and its prevention techniques. Cloning of SRAMs is the most obvious security aspect under consideration wherein the invader can get an easy access to the configuration data. Black box attack is known as the classical method to reverse engineer a chip. The attacker gets access to the system by randomly giving the inputs and analyzing the outputs. Read back is a process which involves reading of configuration data back in order to reconfigure the hardware with a different bit stream. Most of the FPGA families disable the functionality with the help of security bits. It is feasible for the attacker to overcome these security challenges with the help of fault injection techniques. Side channel attack is any attack based on the information gained from the physical implementation of a crypto system rather than brute force or theoretical weakness in the algorithm. Side channel attack detects the regions in power consumption of the device which are correlated with the secret key. FPGAs are extensively used in heavy embedded applications which melts down the possibility of occurrence of such attacks. Block ciphers like Advanced Encryption Standard are designed with a block length of 128 bits and a minimum key length of 128 bits. With such a huge space to explore at hand, it practically becomes unfeasible to perform such attacks. One solution to this kind of attack is to encrypt the configuration file before putting it on the SRAM. This solution involves partly decryption of the configuration file, which increases debugging effort as attacker is known only to the partly decrypted file. Xilinx came up with another interesting approach that combines the encryption techniques with a battery-powered RAM called BB RAM. Hence, Xilinx recommends that the AES key be programmed on the board that has a battery support. The read-back functionality can be disabled with the help of security bits. This method worked well with anti-fuse and flash-based FPGAs where it allowed to load the program onto FPGA under secure environment. Another approach is to use hardened readback disabling circuitry. This mechanism allows readback access to the configuration memory after loading the encrypted bit stream only through a trusted channel, Internal Configuration Access Port (ICAP). To protect the system against the differential power analysis attack, researchers have come across a reversible logic that dissipates zero energy. Another approach is efficient charge recovery logic, which shows 4 to 6 times power reduction with practical loading and operation frequency range. Internet of Things is the interconnection of a large number of resource-constrained devices such as sensors, actuators, and nodes that generate large volumes of data. With this centralized computation of large data, Internet of Things is becoming vulnerable to attacks. With this intent in mind, we are going to discuss the aforementioned key challenges in designing a secure IoT. We will consider an example which will be useful to understand how we overcome this key challenge. Consider a sensor is attacked which now reports erroneous values. This new type of sensing technique incorporates advanced encryption standard to encrypt the sense data, which then sends it to the processor for further analysis. We can think of a situation where one device fakes the identity of another device in the IoT mesh. This security challenge finds its solution in the area of identity of things. The figure shown below is of information stack for identity in IoT. Physically unclonable functions is just like a fingerprint which is unique and is inherited from the hardware structure chip, which is easy to evaluate but practically impossible to duplicate. It is not easy for an IoT object to process something external such as hardware token. However, in some IoT applications, IoT objects such as wearables should be associated to a personal gateway so that the data reaches the destination. Knowledge category also suggests that the IoT object has limited amount of information about the node. Context is based on giving authentication to the gateway for a group of IoT objects rather than a single IoT object. For example, the gateway will authenticate only when the cumulative temperature of temperature sensors in the network is above some threshold. Attackers might attack the nodes which contains the data collected from the sensors, modified and send it to the actuators. High performance counters are registers in commodity processors that monitors the events that occur during the lifetime of a program. If the rootkits are introduced into the system, the difference between the number of events in normal operation and infected operation becomes evident, which then concludes that the data is coming from an infected IoT object. We can overcome this challenge by using advanced encryption techniques which allows the user to authenticate a service before collecting their private data. To make embedded systems resilient to such kind of attacks, it becomes important to test these systems under worst case conditions. In this section, we will consider testing techniques for the IC's processors used in any embedded system. To resist against the hardware attacks, physically unclonable functions must go through these four tests: predictability, collision, sensitivity, and reverse engineering. Predictability test identifies the difficulty of correctly predicting the output for any given input. Collision test studies how often two different PUFs produce same outputs for the same given inputs. Sensitivity test makes sure that PUF works fine even when the components inside the PUF are not functioning properly. Reverse engineering test determines how much intact the PUF circuit components are to the attacks. We saw techniques like real-time IC monitoring, splitting functional blocks into subblocks, and deactivation of hardware trojans to ensure IC protection against hardware attacks. This followed with memory level protection for embedded systems by techniques like AES GCM, AGES, and PAICE. As IC and memory forms the integral part of FPGAs, we saw different types of attacks like black box, cloning of SRAMs, readback, and side channel attacks it may encounter and came up with the respective hardware security measures. With the intention of keeping the above hardware security structure for embedded systems in mind, this presentation discussed about the hardware security measures for this rapidly expanding embedded system application, Internet of Things. Testing of such hardware security measures is of foremost importance. Hence, we concluded our discussion on hardware security for embedded systems with hardware testing techniques. Thank you.